Welcome to our deep dive, everybody. We're tackling algorithms today.
A great choice.
Yeah, our listeners sent in a ton of material, a whole textbook, actually.
Wow.
They really want to understand this stuff, really get a handle on it, so no pressure.
Well, it's true. Algorithms really are fundamental to computer science. I mean, they're the instructions, right? They tell computers exactly how to solve problems.
Okay, so like recipes for computers.
Yeah, recipes, exactly. And just like with cooking, the right recipe can make a huge difference.
So let's jump right in then. Chapter 1, the role of algorithms in computing.
Sounds ambitious.
A little bit, but they start with something familiar. Sorting. Like, we all sort stuff, right?
Oh, yeah, definitely. Files on your computer, books on a shelf, even your to-do list.
Exactly. So the chapter digs into, well, the fact that there are tons of ways to sort things.
And not all algorithms are created equal, right? Some are faster, some use less memory.
Right. It all depends on what you're sorting. Like, a deck of cards is different from a million customer records.
That's where choosing the right algorithm comes in. You got to think about the specific problem you're trying to solve. What's the best tool for the job?
Okay, that makes sense. But how do we know which algorithm is best?
Well, we need a way to measure their efficiency, right? Like, how much time does it take to sort a certain amount of data?
And that's where running time comes in.
Yeah.
The chapter talks about that.
Yeah, running time is important, but even more important is how that time changes as the amount of data grows.
Okay, so like, obviously a bigger data set takes longer to sort. But we need a way to compare that, right? To compare how different algorithms handle bigger and bigger amounts of data.
Exactly. And that's where order of growth comes in. It's a way to describe how the running time increases as the input size grows. We want to see the big picture trends.
So like, is it double in the time? Squaring it.
Exactly. And it lets us compare different algorithms like merge sort. It's pretty good for large data sets. We mentioned that earlier. It has an order of growth of n log n.
Okay, n log n. And why is that better than, say, insertion, sorts n squared? I mean, those sound like math problems, not algorithms.
They kind of are. But basically, n log n grows more slowly than n squared as the data gets bigger.
So it's like one recipe stays manageable even with a huge batch, but the other one explodes.
Exactly. That's why understanding order of growth is so crucial, especially if you're dealing with huge amounts of data. Like, think about Google or Facebook. They're sorting billions of things.
Yeah, so for our listeners out there, if you work with huge data sets, this is for you. Choosing the right algorithm can save you tons of time, maybe even days.
Yeah, no one wants to wait forever for their computer to finish sorting, right?
All right, so we've got our algorithms, they're like recipes, and we know how to measure their efficiency. But how do we know they're actually working correctly?
Good question. That's where chapter 2 comes in. It talks about loop invariants, which are basically checks and balances.
Like making sure the computer isn't cheating at its own recipe?
Yeah. We want to make sure the algorithm is actually doing what it's supposed to do at every step of the process.
So it's not enough to just follow the recipe. We need to understand why each step is there.
Exactly. And loop invariants help us do that. They give us confidence that the algorithm is working correctly.
Chapter 2 breaks this down into 3 main parts, right?
It does.
Yeah.
First, you have to make sure the invariant holds true before the loop even begins. That's initialization.
Okay, so it's good to go from the start.
Yep. Then we have maintenance, which ensures the invariant stays true throughout the loop during each iteration. And finally, termination, which uses the invariant to prove that the algorithm achieved what it was supposed to once the loop ends.
Okay, so for our listeners, this is kind of like a behind-the-scenes look at how the magic happens. It's why you can trust your sorting algorithm to actually give you perfectly sorted data.
Exactly. And it moves us from a how to a why, which is always a good thing.
Absolutely. Okay, so moving on, we've got chapter 3, and it dives into something called asymptotic notation.
Uh-oh. Yeah, it sounds a little intimidating, right? But it's actually a very useful concept. It's all about describing how an algorithm performs as the input size grows really large.
So it's back to that idea of how things scale, like with order of growth.
Exactly. We want to see the big picture, the trends, not get bogged down in tiny details.
And the chapter throws in big O, theta, and omega. Help!
All right, no panic. Think of it this way. You order something online, right? And they give you an estimated delivery time.
Sure, I do that all the time.
Big O notation is like the worst case scenario. It's the maximum time it could take for your package to arrive.
Okay, so like when they say allow 7 to 10 business days.
Yeah, exactly. Theta notation is more like the average delivery time, what you can realistically expect. And then omega, well, that's the best case scenario. Like everything goes perfectly and your package arrives super fast.
So big O is the pessimist, theta is the realist, and omega is the optimist.
Haha, yeah, that's a good way to remember it.
But why do we need all three?
Well, just like with package delivery, you want to use the most accurate information when comparing algorithms. You wouldn't always assume the worst case scenario, right?
That'd make me really anxious.
Exactly. And the chapter warns us about misusing asymptotic notation because it can lead to bad choices. It's like always assuming your package will be late and choosing the slowest shipping option based on that.
Yeah, you might end up waiting way longer than you need to.
And in the world of algorithms, that means wasted time and resources.
So for our listeners, understanding asymptotic notation is like having the superpower. You can see through the complexities of algorithm performance and make smart choices based on your data.
Exactly. You'll know which algorithm will work best for your specific situation.
Now, on to Chapter 4, Divide and Conquer. It sounds pretty epic.
It is a powerful strategy. It's all about breaking down complex problems into smaller, more manageable pieces. Then you solve those smaller pieces and put the solutions together.
So like tackling a giant pizza slice by slice.
That's the idea. Merge sort, which we talked about earlier, is a great example of this. You divide the array in half, sort each half, then merge those sorted halves back together.
Right. And that was the one with the n log n order of growth.
Exactly. And to analyze these recursive algorithms, we use recurrences. It's basically math that helps us express the running time of the algorithm in terms of the running time on those smaller pieces.
Okay, so like a breakdown of how much time each step takes.
Yeah, something like that. It's how we know merge sort is so efficient. And the chapter even shows us this other algorithm, Strasson's algorithm.
What's that one do?
It's for matrix multiplication, those grids of numbers.
I vaguely remember those from math class.
Well, Strasson's algorithm uses recursion to multiply matrices faster than the usual way, like way faster.
So for our listeners, if you're working with those giant matrices, maybe in machine learning or something, divide and conquer could be your best friend.
It's all about breaking things down into manageable chunks and using the power of recursion to get things done quickly and elegantly.
Okay, on to Chapter 5. It looks like we're getting into probabilistic analysis and randomized algorithms. That sounds a little intimidating.
Yeah, probability can be a little tricky, but it's a fascinating area. Sometimes a bit of randomness can actually help us solve problems more efficiently.
Wait, really? Randomness helps?
It can. It's like shuffling a deck of cards to make sure everyone has a fair chance, or randomly selecting people for a survey to make sure it's representative.
Okay, so adding a little bit of chaos can sometimes make things fairer.
Exactly. And the chapter talks about two main things: probabilistic analysis and randomized algorithms.
What's the difference? They both sound kind of random to me.
Well, in probabilistic analysis, we're analyzing an algorithm's average performance. Like, what do we expect it to do most of the time?
Okay, so it's about the average case, not the best or worst case.
Exactly. But with randomized algorithms, we actually introduce randomness into the algorithm itself. Like, imagine you're hiring someone and you have a stack of resumes.
Okay, I'm following.
You could just go through them in order, but what if the best candidate is buried in the middle?
Oh, I see. So you're saying by shuffling them randomly, you're more likely to find the best candidate sooner.
Exactly. So by introducing randomness, we can actually improve the algorithm's performance.
That's pretty cool. It's like a little bit of controlled chaos can actually be beneficial.
And the chapter even talks about randomly permuting arrays, which is basically shuffling elements around.
Like shuffling a deck of cards.
Exactly. And it leads to some interesting things, like the birthday paradox.
A what?
The birthday paradox. It shows that in a group of just 23 people, there's a greater than 50% chance that two people share the same birthday.
No way, really? That sounds crazy.
It is. It just goes to show how counterintuitive probability can be and how randomness can lead to surprising results.
Okay, so we've covered a lot of ground. We've talked about what algorithms are, how to measure their efficiency, and even how a little bit of randomness can be a good thing.
And we're just getting started. There's a whole world of algorithms out there just waiting to be explored.
And we'll be back for more.
Welcome back to our algorithm adventure. We're diving into specifics now.
Yeah, let's see these algorithms in action. Chapter 6 is all about heap sort.
Oh yeah, heap sort. It's a pretty neat one, known for being really efficient, especially in those worst case scenarios.
Worst case scenarios, what does that even mean?
So imagine you have an algorithm, right? And it has a certain running time, like we talked about before.
Right, the order of growth and all that.
Exactly. But sometimes the data can be arranged in a way that makes the algorithm work extra hard. That's the worst case scenario.
So like giving it the most difficult puzzle possible.
Yeah, exactly. And heap sort, well, it handles those tough situations really well. It always performs within a certain time limit, no matter how messy the data is.
Okay, so it's reliable, consistent.
It's a workhorse. And the way it works is by using this special data structure called a heap. Think of it like a pyramid, where the biggest element is always at the top.
Okay, I can picture that. But how does a pyramid help you sort things?
Well, in a heap, the biggest element is always easy to find, right? It's at the top. So heap sort first builds this heap structure from the unsorted data.
Okay, so the largest element goes to the top, then what?
Then we basically pluck that top element off, put it at the end of our sorted list, and rebuild the heap with what's left.
So we're kind of pulling the largest element out, one by one, and putting them in order.
Exactly. It's like having a self-organizing priority list. And the chapter says it guarantees a running time of n log n, which is like the best you can get for sorting algorithms that compare elements.
Okay, n log n. That sounds familiar. So no matter what data you throw at it, heap sort will always sort it within that time limit.
Yep, that's the guarantee. But there's another sorting algorithm, Quicksort, that can often be faster in practice.
Wait, really? If heap sort is the most efficient, how can something be faster?
Well, Quicksort is kind of a gamble. It picks a pivot element and then partitions the data around it. If it picks a good pivot, it divides the problem in half, which makes it really fast. But if it picks a bad pivot, yeah, it can slow down a lot. That's why it's a gamble.
So it's risky, but the payoff can be big.
Exactly. And that's why understanding the expected running time is important. We don't just look at the worst case, we look at what happens on average.
So with Quicksort, even though it might have a bad day sometimes, on average, it can be faster than heap sort.
Exactly. And the chapter gets into how Quicksort works, all the details about choosing the pivot and partitioning the data. It's pretty clever stuff.
Okay, so I'm getting the sense that there's more to algorithms than just finding the one with the best theoretical performance.
Absolutely. It's about understanding the trade-offs, the real-world performance, and choosing the right tool for the job.
Speaking of real world, the chapter also talks about priority queues.
Yes, those are handy. They let you efficiently retrieve the highest priority element.
So like a to-do list that automatically sorts itself so the most urgent task is always at the top.
Yeah, exactly. And heaps are a great way to implement those priority queues.
Okay, so heaps are not just for sorting. They're useful for other things too.
Yep, they pop up all over the place, like in operating systems for scheduling tasks, and even in simulations.
So it's not just about organizing data. It's about managing it, prioritizing it, making it work for us.
Precisely. Okay, ready to move on to Chapter 7 and take a closer look at this Quicksort gamble.
Let's do it. So this pivot thing seems pretty crucial. How does Quicksort choose a good one?
Well, there are different strategies, but one of the most effective is randomization.
Randomization. We're just going to pick a random element and hope for the best.
It's a bit more sophisticated than that. But basically, yeah, instead of always picking the first or last element, we randomly select one. It helps avoid those worst-case scenarios where the pivot is really bad.
So it's like shuffling the deck before dealing the cards. You're trying to make things fairer.
Exactly. It helps to level the playing field and make Quicksort perform well on average. And the chapter dives into the math, the recurrences, to show how this all works out.
I'm starting to see why people get fascinated by algorithms. There's a
Right.
lot of cleverness going on under the hood.
It's like solving puzzles, but the puzzles are how to make computers do amazing things.
All right, Chapter 8. Sorting in linear time, huh? Doesn't that break the rules? I thought n log n was the best we could do.
Well, that's true for comparison-based sorting algorithms, the ones that, compare elements to figure out the order.
Right.
But there's a whole class of algorithms that can sort in linear time, meaning their running time is directly proportional to the amount of data.
Wait, seriously? How do they do that?
They exploit special properties of the data. Like, counting sort works great if you know all your data falls within a certain range. It just counts how many times each value appears and then builds the sorted list from that.
So it's like sorting coins, right?
Yeah.
You just count how many pennies, nickels, dimes, and quarters you have.
Exactly. No need to compare each coin to every other coin.
But there's another one. Quicksort, right?
Yep. It sorts numbers digit by digit, starting from the least significant digit. Imagine sorting words alphabetically, but you start with the last letter, then the second to last, and so on.
Oh, okay. I can see how that would work. So these linear time algorithms, they're kind of specialists.
Exactly. They're super efficient if the data fits their requirements. But if the data doesn't fit, well, then they might not be so great.
So it's knowing when to use the right tool, like you said before. Okay, Chapter 9, Medians and Order Statistics. Sounds a bit more mathy.
Yeah, it gets into order statistics, which is about finding the notheth smallest element in a set of data.
So like if you wanted to find the median salary in a company, but you didn't want to sort all the salaries first.
Exactly. The median is just the element that would be in the middle if the data were sorted. And the cool thing is, you don't need to sort everything to find it.
You don't, but I thought you'd have to at least go through all the data to figure out which one is in the middle.
Well, there's this clever algorithm called randomized select that can do it in linear time.
Wait, linear time. So it can find the median as fast as counting sorts a list. That seems impossible.
It's not. It uses a partitioning strategy, similar to Quicksort, but it only focuses on the part of the data that contains the element we're looking for.
So it's like searching for a specific book in a library, but you don't have to check every single book. You can use the Dewey Decimal System to narrow down your search.
That's a great analogy. And this idea of finding order statistics, it has a bunch of applications, not just finding the median, like identifying outliers in data or figuring out percentiles.
Okay, so it's a versatile tool for analyzing data. All right, Chapter 10, we're getting into elementary data structures now. Back to the basics.
In a way, yeah. Data structures are like the containers we use to organize and store data. They make it easier to access and manipulate that data.
So like file folders or boxes.
Kinda, but more sophisticated. The chapter starts with stacks and queues, which are linear data structures.
Linear, meaning they're like a line.
Exactly. With stacks, you can only add or remove elements from the top. It's like a stack of plates. Last one in is the first one out.
Okay, I can visualize that.
Yeah.
And queues.
Queues are like a line at the grocery store. First one in is the first one out.
Makes sense. So these are pretty simple structures, but I guess they're important building blocks.
You bet. Stacks are used all over in programming languages, and queues are essential for things like tasks.
What makes them so cool?
They're incredibly efficient for searching, inserting, and deleting data. Like, imagine a librarian who knows exactly where every book is in the library.
They'd have to be super organized.
Exactly. And that's what hash tables do. They use a special function, a hash function, to map each piece of data to a specific location in the table.
So it's like each book having a unique code that tells you exactly where to find it.
Yep. And if the hash function is good, you can find what you're looking for super fast. Of course, sometimes you get collisions, which is when multiple pieces of data map to the same location.
Oh, that sounds like a problem.
It can be, but there are ways to handle it. The chapter goes into different techniques, like chaining and open addressing. It gets a bit technical, but the key is to choose a good hash function and handle collisions gracefully.
Okay, so it's all about organizing the data in a clever way to make those operations super fast.
Exactly. All right, chapter 12, we're moving on to binary search trees.
Binary search trees. Are those like regular trees, but with computers?
Haha, sort of. They're more like family trees. Each node in the tree has, at most, 2 children, a left child and a right child.
Okay, I'm picturing it. And how does that help us with data?
Well, the tree is organized so that everything on the left side of a node is smaller than that node, and everything on the right side is larger.
Oh, okay, I see. So if you're looking for something, you can just follow the branches and quickly narrow down your search.
Exactly. Binary search trees are super efficient for searching, inserting, and deleting data as long as they stay balanced.
Balanced, what does that mean?
It means the tree is fairly symmetrical. If one side gets much longer than the other, it can slow things down.
So we want to keep things nice and even.
Yep. And that's where chapter 13 comes in. It introduces red-black trees, which are a special type of binary search tree that automatically balances themselves.
Wait, automatically? That sounds pretty cool.
It is. They use colors and rotations to make sure the tree stays balanced, even if you insert and delete data in a way that would normally make it unbalanced.
So it's like a self-adjusting bookshelf that keeps things organized no matter how many books you add or remove.
Exactly. Red-black trees are a great way to guarantee those efficient operations, even in the worst case.
Okay, so we've got those basic data structures down. What's next?
Well, we're moving on to some more advanced techniques. Chapter 14 introduces dynamic programming.
Dynamic programming. That sounds intense.
It can be, but it's also incredibly powerful. It's all about breaking down complex problems into smaller, overlapping subproblems.
Overlapping, what does that mean?
It means those subproblems share some of the same work. And the clever part is, we only solve each subproblem once, store the solution, and then reuse it whenever we need it.
So it's like having a cheat sheet for solving puzzles.
Exactly. The chapter uses this example of cutting a rod into pieces to maximize profit. It shows how you can break down the problem, solve those smaller problems, and then combine those solutions to get the best answer for the original problem.
So it's about being strategic, planning ahead,